would like you to think about these three things and talk amongst your pod. What do you know about inverses algebraically, graphically, and numerically?
Yes.
Part one, what do you have to tell us? Pick one to explain. Okay, so to find an inverse, we switch x and y and solve for y. Okay? I like it. Part two?
Graphically, it's reflected over y equals x axis.
Okay, Zach does not seem so sure about that. Let's reassure him or tell him he's wrong. Inverses are reflected over y equals x, he says.
That is correct, Zach.
That is correct, Zach. Have some confidence.
Yes.
Okay. Let's see. Part four, what do you have to add?
I'd like to figure out what the definition of numerically is.
Like if I gave you like a table of values, like x, y values, that would be numerically. So what would the relationship be?
The inverse, I think, like the table of the inverse would be just like that.
Okay, so x's and y's switch places. Okay, great. Part five, anything to add?
Nailed it on the head there.
Okay, what was the basic premise of everything?
Y on x.
X and Y switch. Okay, so there is something that we didn't talk about algebraically though. Dealing with the composition. Composition. What happens when you compose f and its inverse?
Oh, they equal 1.
Almost.
Equal 0.
Almost. They equal x. Okay, so this is the definition of an inverse. If you take f composed with its inverse, it should be x. Okay, so if you have two functions where you do both of the compositions and they equal x, then f and g are inverses of each other. Okay, you spent some time in Algebra 2 doing that. You spent some time in pre-calculus doing that. All right? That is the definition of an inverse. Okay? Yes, x and y switch places, and that's how we recognize inverses. But to prove that two functions are inverses of each other, you would take their composition and make sure they equal x. Okay. When we were doing inverses in my pre-calc classes, I had some students always refer to it as one is undoing the other. Okay, and I think that's a great way of thinking of that. That's why, you know, our composition is x. Okay. All right, so as Zach said, with confidence, when we look at this graphically, our inverses are reflected over the line y equals x, okay? And when that happens, right, our x, y coordinates switch places, okay? These are all things that we've talked about before. What? Nope.
Come on.
We eventually, okay, what have we been working with this entire unit? Derivative. So eventually we're going to be able to find the derivative of a... Okay. So here we go. If we were just going to look at a graph, how do we know whether we are going to have an inverse? Okay, a vertical line test tells us if we have a
Function.
function.
Horizontal
Okay.
line test tells you whether or not you have an inverse.
Okay, a horizontal line test will tell us if we have an inverse or not. Okay, so let's think about y equals x squared, right? Does this pass the vertical line test?
Absolutely.
Yes, so it's a function. Does this pass the horizontal line test?
Unfortunately, it doesn't.
No, okay? If we graph the inverse, we get this. And is this inverse a function?
Not a function, but it's an equation.
It's an equation, but it's not a function. Therefore, the inverse doesn't exist because the inverse is not going to be a function.
So what did you say?
Okay?
The inverse.
So,
Yeah, you can't do
does this pass the horizontal line test?
Absolutely no.
No.
Oh.
Does this pass the horizontal line test?
Yes.
Okay? Does this pass the horizontal line test?
Yes.
Okay? So let's think about these three graphs that I wrote up here. What is causing that first one not to have an inverse?
There's more than one. Actually.
Okay, so it's not passing the horizontal line test. Okay. These are on powers. Okay? What's different about that than these?
Oh, the second two have no horizontal derivatives or derivatives that equal 0.
Okay, so these don't turn, right? Okay, notice how this one is always increasing. This one is always decreasing. Okay, we have a special word to describe those kinds of functions. Okay. So first of all, back to the horizontal line test. These two pass the horizontal line test and the vertical line test. That means our function is 1-to-1. You've heard that before, right? We mentioned it in pre-calculus last year. I know we did. I know we did. You may have not put it in your brain. Okay, but if a function passes both the vertical and horizontal line test, it's 1-to-1. There's one x for every one y. That's it. End of story. Okay. Now, the second part of this theorem says if f is strictly monotonic over its entire domain. Wow, what does monotonic mean?
One atomic.
Okay. Care to elaborate? Okay. These two functions right here are monotonic because this one increases across its entire domain. This one decreases across its entire domain. Okay? Therefore, they are monotonic. So if a function is monotonic across its entire domain, then it's 1-to-1, which means we have an inverse. Okay? It's going to pass the horizontal line test. If it's always increasing or always decreasing, then it will pass the horizontal line test because there are no turns. Yes? 1-to-1 means our graph passes a horizontal and vertical line test. So it's a function and it has an inverse. There's one x for every one y. Okay, so, yes.
I just have one question. What if you have a graph that goes like this, hits a 0, but then goes right back up?
Well, okay.
Can I draw it?
Well, no, I know what you mean. I'm trying to think of a good answer for you.
Can you draw? Good.
Why?
I think we'll do it.
Like that? Well,
Well, I mean like sharp tighter, but sharp. Okay. So,
Yeah.
Well, if this is for more than just 1 point, then it's not
oh,
gonna
just
pass
for 1
the,
point, just for 1
just
point.
at 1 point, so you have a horizontal tangent,
At 1 point.
right.
Yeah, something like that.
Then the inverse would still exist. You would just have a vertical tangent on your inverse function.
Okay.
Okay, so why are we talking about all this right now? What do we know about functions that increase? Their derivative is positive. What do we know about functions that always decrease?
They're negative.
Okay, so if our derivative is positive across the entire domain, right? We know that that is increasing. If we know that our derivative is less than 0, then we know it's decreasing, right? Okay, so I am going to give you some equations where I'm going to ask you, does the inverse exist? Now, there are you have found inverse equations before, right?
Yeah.
Okay. Not all the time is it practical or possible for us to find the equation of the inverse. Okay, algebraically, they're going to be pretty hard to solve. Okay, so first of all, we need to be able to tell if the inverse exists, but I'm not necessarily going to make you find the inverse equation. Okay, so here we go. We know the answer to this right now. And what's the answer to this? No, because we know it's a parabola, right? But let's just, knowing that this should be, no. Let's think about it with calculus, okay? What is the derivative of f?
2x plus 2.
Okay, so what we need to ask ourselves, is this derivative always positive?
No.
Is it always negative?
No.
No. Sometimes it could be negative, sometimes it could be positive. So this is not monotonic. So the inverse doesn't exist. Okay.
So if it doesn't pass the horizontal line test automatically, it's just can't have an inverse.
Exactly.
Wait, so like there is an inverse, but you can't use it.
There isn't an inverse. We could draw the graph, but it's not a function, and so it's not an inverse. Okay. Yes.
Why is it not monotonic?
Because, okay, so the domain of f is all real numbers. If I plug in values, sometimes I can get this to be negative. Like if I plug in -3, this would be a negative value. But if I plug in 5, it would be a positive value. So since it's not always positive or not always negative, then it's not monotonic. Let's do this one.
Oh. No, she did. She did.
Okay, so first of all, I want you to imagine switching the x and y's and solving for y in this example.
Oh boy.
Right?
Why do you? No, he wants to.
Okay. So let's look at the derivative. What is the derivative? 3x squared plus 1. And what do we know about 3x squared plus 1?
Always positive.
It's always positive. No matter what you plug in for x, that square is going to make it positive. And then we're adding 1. And so it's going to make it even more positive. So our derivative is always positive, meaning it's monotonic. And therefore, our inverse exists.
Well, I don't know if it's not one of those ones that like goes like that.
Because we're always increasing. If our derivative is always positive, we are always increasing. Okay, that's the point of this right here. Okay. All right. So now
one didn't exist, could you plug in 0 to 3x squared? 'Cause what would that mean?
Okay, say your question again.
Like, in the equation, the derivative, if there wasn't a 1 and you just had 3x squared, you could plug 0 in and it would equal 0, so what would that be?
That's kind of like the case.
Right. And that would, since it's only 0 at 1 point, it would be okay.
Zero
I would actually
neighbor.
do it.
Yeah.
Anyways, it's
Okay, I am going to give you the rule for the derivative of an inverse, and we're going to talk about why. Okay, so this is F inverse derivative is 1 over F prime of F inverse. Okay. Some of you don't care, some of you do. Why is this the rule? First of all, let's think back to what the definition of an inverse is. The definition of an inverse is when we take F composed with its inverse, we get X. Okay? Excellent. Let's take the derivative of both sides. Chain rule. So on the left side, when we take the derivative, we get F prime of whatever's inside times chain rule, derivative of the inverse equals derivative of the right side, 1. Alright, so we just took the derivative of both sides. Okay, so now if I solve for F inverse prime, then we would divide this over. There's your rule. Okay? Now, does this look like a simple rule?
No.
Okay, it's a simple rule, but for some reason it is difficult to remember. You have to do your homework today. Okay? You have to practice these. Okay? Let's try a couple.
Well, I'm stuck.
What? Okay, so we want the derivative of the inverse evaluated at 3 when we know that the function is this. Now, first of all, okay, there are times where, yes, we can find the inverse, take that derivative and evaluate it. But right now, we don't have the, we can't find the inverse of this. Okay? Icky. Alright? So, we have to use our derivative rule, okay, for just evaluating that equation. Alright? Well, we need to know some information about f of x. If we are evaluating the inverse at x equals 3, 3 corresponds to what kind of value for our function? Our y value. Okay, so we need to know f of what value makes 3.
So how do we know that?
Okay, so if we're
Oh, because the derivative is a.
we're evaluating the derivative at an x value, right? So if our x value is 3 for our inverse, that means our y value is 3 for our function. Okay? So we need to figure out the value that we plug in to make f of x equal 3. Nope. Basically, right now we need to play around with some numbers. Some numbers to try. 1, 2, 3.
5, 17.
I'm stick with like 1, 2, 3, positive or negative.
Probably the inner
Well, I would say not -1 because you have a fraction.
Probably one.
4 cubed would be 64, divided by 4 is 16, plus 4 is 20, minus 1 is 19. Or not good.
The X.
It's all
2,
That sounds pretty good.
2 cubed is 8, divided by 4 is 2, plus 2, minus 1.
got a
Two, yeah.
So when we plug in 2, we get a value of 3. Okay? On your homework, there are some that, okay, because we could make a side note here. You can try to plug in that value for y. In this case, we're not going to solve that equation. If it was a quadratic, that'd be cool, but it's not. If it's a quadratic, you can plug that y value in and solve it. If it's linear, obviously you could too, okay? It's not going to be quadratic because they don't have inverses, okay? So if it's something you can solve, go for it. If it's something you can't solve, do some guessing and checking until you can figure it out, okay? I'm going to tell you the problems that I give you. They're going to have a range from -3 to 3. 1, 2, 3, positive or negative. Try those numbers. Okay, maybe 0. Yes.
Can you show how you got to?
Honestly, we just plugged in some numbers until it worked. So if we plug in 1, we can see that we're not going to get 3. If we plug in 2 to x, we get a value of 3. We just did some guessing and checking. Okay? So we know that f of 2 is 3. What does that mean about the inverse? F inverse of 3 is 2. But that doesn't really matter because we want the derivative of the inverse.
Oh,
Okay.
no.
So, the inverse derivative is 1 over f prime of the inverse. Okay? So what do we need to know about f? We need a derivative for f. So what is f prime?
3/4 squared.
Excellent. Okay. Now what do we do?
Have to plug in the composition.
We need the derivative where? Okay, so let's do this. The inverse derivative at 3 is f prime evaluated at the inverse at 3. Right? F inverse of 3 is 2. So we are basically plugging 2 into our derivative. Right? Do I need to write that second? And what is f prime at 2?
Four.
Okay, so let's sort this through. Okay? We took the derivative of f, right? Since we're evaluating the derivative at 3, right? For our inverse, we plugged in 2 to our derivative, right?
Say you evaluate the inverse at inverse number plugging the derivative.
Right, like that's what we did here, right? Because down here, our rule is the derivative evaluated at f inverse, right? So we figured out, well, if we're evaluating at 3, that means the y value is 2. Because on our original function, we have this 0.23. Right? I'm getting either blank stares or yeah, I gotta go into the next one. I can't read it.
There's another example that helps.
Would you like another example?
Yes,
Okay.
please.
Here I actually tell you what the point is. Okay, I want the inverse evaluated at 7,1 when our function is 7x cubed plus the natural log of x cubed. Okay? We cannot solve for this inverse. So in order to take the derivative, we have to think about the derivative of the original function. If we are evaluating the derivative at 7,1, what does that mean about our function? We have the coordinate 7. Let's also talk about the derivative of our function. Yay. What's our derivative? What's the derivative of 7x cubed? Plus 3 natural log of x squared times derivative of the inside 1 over x. Okay, the natural log of x is being cubed, not the x. Okay, that is how you run it, right, Zach? Okay. So now, if we want, sort this through, if we want the inverse derivative, then what do? 1 over the derivative of the inverse, okay? So we're evaluating the inverse derivative at x equals 7. That's what I really wanted to write there. Okay. Well, what is f inverse of 7? 1. So what we're really doing is taking 1 over the derivative of 1.
You put those around, didn't you?
We want the derivative at 7,1.
Okay.
So we're finding f inverse derivative evaluated at 7.
It's just like a little add-on. Or do you have, why'd you put one?
Well, because that's the coordinate that would be on that one.
Well, the inverse is
So 71 is the inverse point, or is it the point?
That's the coordinate on this function.
Yeah, so is 71 an inverse point?
7,1 is the inverse point, and that's where we're evaluating the derivative. Okay? So now, when we plug 1 into our derivative, what do we get? The natural log of 1 is 0, yes. So we have 1 over 21.
What'd you put the 72?
Well, it's just the point. We know the inverse at 7 is 1. The inverse at 7 is 1. what I'm kind of hoping that you figure out is that this is always gonna be what? Well, it's always gonna be the other number in your coordinate, right? So really, I mean, this, what you're plugging into the derivative is always the x coordinate on your function, okay? That, I think, makes it easier. If you can recognize that this is just the derivative evaluated at your function x value, okay?
Morning, this is Mr. Steele, Assistant Principal of Cleveland Vista South High School. I need to see the following seniors in my office at this time, with my thanks. Graham Brooks, Kelsey Lang, Shirley Conway, Lizelle Hampton, and Madison Finley. Thank you. And stand by for announcements.
That makes me a little nervous.
Hello and good afternoon. It is now time for your Titan student poll quiz.